classify universality classes, which in equilibrium means we want to classify conformal field theories. And we have adopted the strategy, and we want to do this, clearly there are two main tools to do this. One is directly to work in conformal field theories, and this is what we use to classify conformal field theories in 2 dimensions. But this is actually quite complicated when you go to multi-component and to many symmetries. And then in general, what we ask is, in particular in 3 and 4 dimensions, which are the possible non-trivial fixed point of the renormalization group. So the strategy that we adopted is the one of using the Epsilon-Expansion, which means that we are making an expansion around the critical dimension. Okay? And we did this with a novel technique. So what we present here is a new approach, which is called the functional perturbative RG, where basically what we do is to work functionally. We do not work anymore just with beta functions. That is the standard things that we compute, but we have seen we work with beta functionals. And beta functional have many interesting properties and simplify and clarify a lot the discussion. And what we came to after the first 2 lectures is to this map. This is a table that we explained that it could be generalized to any loop order, and at any loop order there is a certain set of upper critical dimensions that appear. Okay, and in particular upper critical dimensions are in one-to-one relation with universality classes when we speak about one component. And then we saw that in dimensional regularization, the functional form it can be determined in a very simple way without having to do any calculation at all. And then this left us with the game of finding a simple way to fix all the coefficients. And yesterday we spent some time to do that. And so now one of the messages is that, as you see, there are only 3 universality classes that already appear at one loop. Most universality classes appear at higher loop order. Okay? And for example, if you look at L equal 2, for example, the 3 critical universality classes, the first non-trivial RG information is encoded in divergences of 2 loop diagrams. For example, if you look at this one, which is one of the universality classes that we uncover in our works, it's a universality class that has another peculiarity. It has a fractional upper critical dimension. And so to see some non-trivial RG information for this universality class, we have to look at 3 loop diagrams in fractional dimension. And in this way, we find the RG information from which then we can derive all the properties. And this map can be made, we learn how to make it systematically. If we add the 4 loop column here, there will be new upper critical dimension that appear, and this will have functionals that we can compute and so on. This is the functional for the potential, it's the beta V. And then we have a functional for the wave function or normalization function, okay? And we can do the same kind of analysis. Then we saw that the key point is that one of the reasons why this approach is very convenient is that normally when you work with the generating functions allow you to obtain a lot of information in a very simple way. And in fact, beta functionals are generating functions for the beta functions. Okay? So, for example, now we focus here as an example to see how from that table we can deduce all the properties which can be deduced in the Epsilon-Expansion for the theory, and even some new ones that were not known in the literature, in particular the OPE coefficients. So these are our beta functional leading and next to leading order, and also we remark that it's only the leading and next to leading order which has universal coefficients. Okay? And then what we do is to switch to dimensionless variables. Okay? So this is the place where both the anomalous dimension and the epsilon of the Epsilon-Expansion comes to the game. And then what we do is to make a Taylor expansion. Okay? By making a Taylor expansion, we decompose the potential into the couplings. Okay? Now, if we insert this expression inside here, on the left-hand side, we will have a sum of beta function times some field power. And also the right-hand side will have the scaling with the classical scaling plus eta, and then the nonlinearities of the renormalization group that comes from these terms. So you expand and then you equate single powers of the field, and you obtain in a very straightforward manner all the beta function, and as we said, we are focusing on the relevant and marginal sector of the theory. For example, just to make you see that here you recover the one and two loop computation that you may have done, but we have done it in a much more simplified way, actually not even, without even using a 5 to the 4 theory. This was one of the comments. But at the same time, we realized that all the information there is, all the RG information which you can find in perturbation theory actually depends on only those 3 numbers that we computed yesterday, A, B, and C. And from that numbers, we derive all the information. Okay? So once you have this, so in this case, you see you have the beta function for the mass. When you go in every quantum field theory course, what we normally do is to make 2 different computations. One for the coupling and one for the mass. And then if I tell you, let's look at, I don't know, a node deformation, you will do another computation. And every time you will compute Feynman diagrams. And actually, there is no need to do that. Because the RG information, the universal data is very specific and can be triggered down for any universality classes that way. At the one component case, the quest for finding universality classes is trivial. There is only one fixed point for one universality class. That's the reason why universality class has one-to-one correspondence with the upper critical dimension is. What we're going to start today with the multi-component world is where the nice game of classifying universality classes becomes interesting. But at this point, we have one fixed point, and then we expand around the fixed point. And so the RG, the universal data, the RG information, which is also the CFT data of the theory, it's manifest. Okay, so we know that the scaling exponents, these are the RG eigenvalues, which are invariant. They are directly related with the scaling dimension or with the critical exponents. But then we also have the OBE coefficients of the critical theory, so the Gaussian theory. And also what we find is a first correction in epsilon. This was a novelty that was never seen before. And yesterday we discussed it a lot. How much can you characterize OBE coefficients in the epsilon expansion, and how this calculation in the RG can be matched with the one that we also did in the analytical bootstrap. And then, this were okay. And then we saw that for any universality class in our table, we can do the analysis and we can go in depth. In particular, we focused on this new universality class, and we discussed how we could characterize this universality class also with other non-perturbative approaches. Because this was one of the novelty of what we did up to now. So this is a very short summary of yesterday, and in any case, now our quest now starts to go in the interesting part. Now we want to find universality classes for an arbitrary number, for n, the number of components, which is bigger than 1. Okay. Now, in principle, when you, for example, if you have studied the Ising model, the theory, the 5 to the 4 of the Ising model, and you want to go to study the ON model, normally what you do is to start over, and you will do computation again. You will start looking at the diagrams. You will write the Feynman rules. We write. There is no need to do that. That's all wasted time, because the beauty, and actually I think this is the single most valuable thing that this approach brings, is that now when you want to work in the multi-component case, the table of universality classes basically gets promoted with basically no effort. And this is very simple to understand, because we have seen that, for example, the beta functional for the Ising model is equal to 1/2 v second square minus 1/2 v third square v second. Okay? Now, this is in the single component case. If now I go to have something with multi-components, then my potential will be a function of all the components of the field, and the Hessian, the propagator, the vertices will be constructed using general vertices. Okay, where this thing means that we are taking derivatives with respect to phi I, phi j, and so on of the potential. Okay, but now if you look at the discussion that we made, and you want to see in how many ways can I promote this when there are more components, you realize that for the unitary family, so those which are actually the one which interests most to us, those with upper critical dimension 4, 3, and 8/3, you do not need to do any novel calculation because there is only one way to promote this thing. And here there is also only one other way to promote this quantity, okay? In the case of the non-unitary family, okay, at the leading order, there is only one way to promote it, okay? At the next to leading order, there is a degeneracy. So that, for example, this was the next to leading order contribution to the Young universality class. Now, when I have a V3 second and 3 V seconds, there are actually 3 different contractions. So in this case, for the next to leading order in the non-unitary family, we have only one constraint, and so we really need to make some additional computation. But for the leading and next to leading, so which means all the information which is universal in this family, which is the one that interests us the most, there is no need for any additional computation. So this means that in a switch, or in the blink of an eye, we have some master functionals. We have some formulas for the beta functionals of the leading and next to leading order, which apply for any number of fields, which means they can support any symmetry. So it means that basically this means that the RG information and the group theory information, the RG information and the symmetry information get decoupled in perturbation theory, dimensional regularization, Epsilon-Expansion. So it means that you only need, in particular if you focus in 4, you only need these 2 coefficients, and if you remember we compute this one, this is just the vacuum energy of a free scalar, and this was just one diagram that we need, and this one we obtained it by a scaling argument. So whatever theory you want to study in 4 dimension, the scalar sector of this theory could be the scalar sector of the standard model or whatever model you're studying. You don't need to do anymore a loop integral because the information is only these 3 little numbers. The rest is all the symmetry part, the group theory part. And so this is even more impressive when we go to the higher multicriticality, because for example, the D equal 3, which is the 3 critical universality class, so it's the second one in the family of the unitary case, also gets promoted, and there is only one contribution. You can obtain all the terms, and these things start to be completely non-trivial. And these things start to be something that is equivalent to, for example, a for-loop computation, because this was a for-loop computation that you remember we derived the form of these things by our dimensional analysis and with a little bit of topology. And once the coefficients are fixed with one strategy or the other one, okay, then you have this one for any theory, and now this starts to be completely non-trivial information. So for example, with this one, we will study the tricritical ON model, which has a large N limit which is completely non-trivial. And to be able to see the signature of this large N limit, you need to have the leading and next to leading order. Something that before, if you wanted to do the old style, you will have to attack a lot of for-loop diagrams to obtain the same information. So I would say that this is really the most interesting thing that the functional perspective brings, even more than the one of having access to the OPE coefficient and for an overall simplification of the calculation and the structure that we wrote down. And we can go on, because for example, this is the tetracritical universality class, and you see that these are 6 loop terms even, and we have everything there. So we don't need to do Feynman diagrams anymore if our interest is finding, classifying, and constructing universality classes around their upper critical dimension, which, as we said before, in the general picture, we expect a universality class. If this is the dimensionality, we expect a universality class to exist from its upper critical dimension all the way down to 2, where normally this is a minimal model in conformal field theory when we have one component. And then we are interested in the cases where we intersect some other integer dimension. Okay, so for all this structure that we understood, even in the multi-component case, we have complete access. So this really completely somehow revolutionizes our point of view on how to do RG computation. Now we don't have to focus anymore on diagram, on the calculation of beta function. We focus more on which are the symmetries and which are the invariants that can carry that symmetry. Because the structure of the invariants will dictate which is the upper critical dimension, the first upper critical dimension in which we can have a realization of that symmetry. Okay? And then we can have even more. This is something even more. We really have we have general formulas that we constructed for this thing. So we really have any theory can be done. And this is something that you can just program inside. But the problem is that you really have the job is done. And for the even models, we have both leading and next to leading order, which are fixed. For example, this is an 8-loop calculation. Maybe next week we're going to go through the beta function for the ON model, because there is really an interesting thing which is not yet understood, is really the large N behavior of the ON models. There is the phase diagram has a strange structure, and this is a subject that can be attacked with this, together with the non-perturbative formulation like the one that we saw yesterday. Okay. No, this is the one that contributes to the anomalous dimension.
Okay.
So this one is for this one. So this is external legs. Okay. Or it's a non-zero field. Okay. And while for the other family, for the family which is odd, instead we have blocked only the leading order contribution. The next leading order contribution is more needs an additional computation of some kind. But it's already very interesting for our theory, the 10/3 theory, because here you see it's already the leading order is quite involved. And somehow, for the odd family, the leading order is as complicated as the next leading order of the even family. And we saw that, in fact, one can obtain some contribution from the other one by using a continuation. Okay? Okay. Okay, so now, so this is basically let's say the main theorem for the main theoretical result is the fact that we're able to do this. Now, what we're going to do today and the next week is using this tool for asking questions about universality in the multi-component case. So now I want to do something a little bit more practical in the second part is, okay, let's then study the ON model, okay, which we know very well, but let's see how it can be derived from our master formulas, okay? So, is there any question up to now? Something? Okay. So in the ON, so now we have a field which carries a representation of ON, okay, and we have that our action is so the ON invariant cinetic term. Okay, and then there is our potential, which now the first thing we need to do, and in the case of the ON is basically trivial, is to start speaking about invariance, because the potential is, so in general we write the potential in terms of phi 1 to phi n, but we should rewrite this one in terms of a set of invariants, rho, tau, sigma, and so on, which transform according to the symmetry that we are imposing on the problem. The ON symmetry is so strong as the sphere, which only has one invariant, and the invariant is normally, we call it rho, we call it 1/2 phi I phi r. Okay, so it's just the square. So it means that the potential, we are going to write the potential here in terms of u of rho. Okay? Now, the beta functional, as we have seen, is only this expression here. So what we need to do is to just convert this expression into an expression for the potential U of rho. We can do that, and now we're going to do it so that we also do some exercise, and it's not just like a seminar. You do that, and this thing here transforms into this one. And so this is the beta functional for the potential of an ON theory. And you see that there is a typical term, because we have the radial and the two modes, typical modes of the ON model, and one disappears when we go to n equal 1, okay? And so when n is equal 1, this is just a rewriting of the one for the Ising model. This is interesting, first of all, because of its generality. Second, it is interesting because this can also be the starting point for asking questions to the flow of the potential of one model, a la Coleman-Weinberg, for example. So now we will focus on beta functions. But this is the flow of the potential in the ON theory, and we can integrate the flow of the potential from the ultraviolet to the infrared. And you, for example, can study how the potential develops its convexity, if it is possible, and all other kind of things. And in the same way, we have the eta, okay, which is given by this formula here. Okay, there is a factor of n because in the multi-component case, if you see, in the multi-component case, beta functions for Z have two indices. So now, this is a peculiarity of ON model, is a peculiarity of other fixed point. The anomalous dimension matrix, okay, is proportional to the identity. Okay, while we will see that there are universality classes, and in particular in 4 dimension we have found some new ones which have the anomalous dimension matrix, which is clearly diagonal when it's diagonalizable, but it's not proportional to identity. So there are more than one anomalous dimension. But when this is proportional to the identity, here there is just a delta, and then you trace on the delta, okay? And this trace on the delta will give you the n on this side and take it on the other side, okay? And then the eta is minus the beta z, so the famous 1 over 6 becomes minus over 6 becomes 1 over 6, and you see that now this is completely contracted. Again, now and then now we're going to do this little computation, and this expands into something of that form. So in this way now we're going to reproduce all the critical information of the ON model. Okay? And in particular, then we can even do new kind of studies. So let's just see in practice. Let's just go through. So this is more as an exercise, but so it's really simple. This is also the schema for when you do an arbitrary theory. What you do is that, okay, here we write the derivative of u with respect to function of, and you get these very simple expressions. Okay, you normally introduce a projector operator, which is the projector on the transverse and radial modes. And so the Hessian is actually written down in a very simple form. And in this form, it allows you to make, if you want, this also allows you to make inverted, even if here is not necessary. And then you compute the square and you trace it. Okay? And then you say, okay, let's compute the free vertex. So you compute the free vertex, okay, and the free vertex will have these two tensor structures. Okay? And then we can also do some manipulation in such a way that we can write it in terms of the projector. This is just, I mean, you can just do this by putting it into Mathematica and not even close your eyes, but you can go through the structure very easily also by hand on a piece of paper. And just to give you an intuition also how it works in general. And so, you see, we can have some nice expression for the third, and then the same thing for the fourth vertex. So now you just do some little algebra, you exploit the fact that clearly this object and this object are perpendicular to each other, so their product when they are traced multiplied is 0, and you obtain these terms here. You put everything together and you have your beta function. Okay? And this is all that there is in the relevant and marginal sector of ON models for an arbitrary n. So now that we have the beta functionals, then we have to do like we did in the other cases. We go to dimensionless variables, okay? And so we go to dimensional variables in the standard way. The key is the dimensionless field with the proper factors, and so your expression. So this is the ON version of the equation that we studied for the Ising model. Okay, there is it's very simple. Now you can do the step of going to the beta functions. So in particular, just to as a standard application, we take the potential that has a mass term and has a quartic coupling. You plug them inside, and this will generate all the combinatorial factors that normally come out from the analysis of the diagrams. Here they are all generated by basically computing these products of U and these traces, which are the general formula for the beta function. You use this contraction and you find all the relations. And okay, then we go on, and then at this point, this is still a theory with just one invariant. It's a theory with just one coupling, so it's as complicated as the one component. So the fixed point again is trivial to obtain. There is only one fixed point, and the fixed point is this expression here. At this point, you do the standard analysis that you compute the stability matrix. Stability matrix. You will diagonalize the stability matrix and then evaluate it at the fixed point, and then this will give you the RG eigenvalues. The RG eigenvalues are directly related to the scaling dimension. The scaling dimension are directly related to the critical exponents, and you obtain your formulas for example, eta and nu, which are the critical exponent. Then, for example, also your formula for omega. Clearly, this expression for n equal 1 will reproduce what we did yesterday. And now this is, this is the outcome of the ON analysis. Okay. So what I want that you appreciate here is that it basically comes for free. Okay, it comes for free in our general framework. Now, when we study now, the nice thing is that the ON model is already strong enough to characterize and describe various types of universality classes. And in particular, apart the finite n, now this is something you have already seen, and I will not go through the details, but n equal 1 is Ising, n equal 2 is a specific problem, which is the XY model, n equal 3 is the Heisenberg model, which is also very important from an experimental point of view. But then it's very interesting because both the n and large n limit, really the large n limit is the so-called spherical model that has a set of critical exponents which are clearly reproduced by our formulas. But what is more interesting is the fact, for example, that the n equals 0 limit is reproduces the universality classes which is related to self-avoiding random walks. So this is a very nice part of statistical mechanics. Self-avoiding random walks, they are random walks where the walker cannot cross himself. So there is a non-local type of interaction. So this problem is much more complicated than the Gaussian random walk, which is described by the Gaussian. This is Gaussian. This is Gaussian universality class, and this is the self-avoiding random walk universality class. Actually, it was Charles de Gennes who was able to describe and prove that the criticality of the self-avoiding random walk could be described by the n equals 0 limit of the ON models. So this is really, the beauty of the subject of universality is that we are using the language of quantum field theory. But in reality, we are describing a lot of critical phenomena in nature. And also the other example, typical example of the use of the normalization group, which is the one related with the Potts model and percolation, has a map of the same kind. Okay? Yes. So this is the ON model, the Now, I didn't prepare it for today because I want to show you a mathematical code next week so that we see some new result. We really do the computation together. So next week I wanted to make it a little bit more applicational and also maybe some also research problem or try just to see something, no? Because this week with this, basically with the master formulas, we have derived all that there is. It's only a matter of studying the systems, okay? But in any case, also for the ON model, so this is this equal 4 is the standard ON. But then we also have, if we now we're going to apply the formulas to be and obtain what is called the tricritical ON. Okay? And the tricritical ON has a non-trivial large n limit. This has a large n limit which is trivial because it's just the spherical model. With critical exponents you see which become trivial quantities in a sense. But this large n limit is much more interesting. And what I have been studying and is actually still quite an open problem is to, so then we have the tetra, so we have, and this is the penta. So these are the, you know, when we discussed the other day the map of the multicritical Ising models, we saw that they were, you know, this, in the case of, so this is the case of ON. And when we look at the case of Ising, the critical version, they were in 2D, they were minimal models, and they are, what are they, 3, 4. This is the model, I think it's 4, 5, and this is the 5, 6, and this is the 6, 7. No? There is this family that was found by Zamolodchikov. So this is how these models, they look in 2 dimensions. Now, for the ON models, there is the Mermaid-Wagner theorem that tells you that they do not exist in 2 dimensions, but they exist in 3 dimensions, or they exist in all the region between, okay? So now, these universality classes that now we have access to them, because we just need to go through with a mathematical code with the same kind of manipulation, but apply them to the more complicated functional. This will give us a set of beta function and then a set of critical properties that actually describes these theories. And these theories are somehow the ON version of the multicritical models. Now, the Mermaid-Wagner theorem that perturbation theory cannot show us, but the non-perturbative RG can show us, and this is one very interesting things that maybe I will show you, do not exist for n bigger than 1, but they can still exist, for example, for n equals 0. So these actually are, this theory here in the n equals 0 limit, they are basically corresponding, and this is my conjecture in a sense, to a more complex type of random walks in 2 dimensions. And this is the first characterization of that. So this is just to show you how many directions you can use these tables and to explore the various things. Okay. In any case, all this material is completely new because nobody will somehow with the standard techniques nobody will attempt. This is the loop order. Here is 2, here is 4, here is 6, and here is 8. Nobody will waste a PhD to compute the beta functions at 8 loops for a model like this one. But now that you have it for free, you will explore that. Okay? And again, there is the fact that it seems that the large n limit for these models is non-trivial, while it's trivial for this one. So for the odd powers, okay, so these are, if you want, these are based to 5 to the 4, these are based to 5 to the 6, this is based to 5 to the 8, these are based to the underlined here. So for these ones, the large n limit is trivial, like we have seen, but for this one, the large n limit is not trivial. And actually there is some work that shows that this large n limit, there is a line of fixed point at large n, which the BMW fixed point that has it was seen in the past, and now there was some recent research. So even there are even things to uncover in the phase diagram of ON models that it's something that you think, no, it's everybody knows that, we have understood everything. It's not really so, okay? Because exactly like In the case of the one component, understanding Ising is not all, even for sure is the most interesting, most relevant part in 3D, but all the complexity of the structure of the phase diagram has something also in the ON model. So this is a kind of things that you can do. And again, what is really important, and now your focus goes not anymore in doing the computation of the beta function, but studying and asking questions. And in particular, this is what I want to do, just to make a summary. This is now current research. So for example, now we can look at leading order, the critical model. You have this, we have already computed these quantities, we just need to make different kind of traces of the same quantities, and we have, these are the leading order beta functions for the critical ON model. And okay, and here is where we can do, so one thing that we did in this paper was, okay, there are various interesting things, because again, exactly like what we said yesterday, we understood the picture of one component universality classes with perturbation theory, and we understood with non-perturbative techniques like the non-perturbative RG, and we understood with the analytical bootstrap, with the Schwinger-Dyson plus conformal field theory equations. No? So we want to have, for any problem, I like to have, it's always good to have different perspective of it. So actually, we were able to see this critical version of the ON model exactly like I explained yesterday with the non-perturbative RG. We were able to see the multi-critical models. And actually, this is a tool that allows us to control the system away from the upper critical dimension. And in particular, this is interesting because for the ON model, the non-perturbative RG should be able to encapsulate the Mermaid-Wagner theorem. And in fact, you see that the fixed point, which exist. So for example, if we plot the anomalous dimension, so what we did, one can make a plot like this, write eta, and here you can write d. And so you can have 4, 3, and 2, okay? So you will find that now, if you will find a curve that goes like this. So this is n equal 1, okay? And then, so this is the value of the Ising model, which is 0.0036, and this is 0.25. Okay. So this is the n equal case. Then you see the other one, and what is nice is that, okay, the epsilon expansion gives us the first part of this curve, okay? Then we have already discussed that, okay, maybe in 3 dimensions you can have some values, but the epsilon expansion is not a good quantitative tool, apart for probably this particular universality class, which has epsilon equal to 1/3, which is not. But in general, it's not. In general, we need another approach, and we discussed that either we do it with the bootstrap or we do it with the non-perturbative RG. We have some. But now, if this thing goes, and I can prolong it, I have a question, because I know that the Mermaid-Wagner theorem tells me that there is no fixed point with continuous symmetry in 2D. So something should happen. And what was really nice of this work, that we make a PRL on that, was that exactly the non-perturbative RG was able to bend down and go to 0. So which means that if you give to the RG enough space, you don't truncate it just at the level of beta function, but you give it enough space, he is able to encode and reveal also some non-perturbative theorem as the Mermaid-Wagner theorem is. And then this happens with all the, sorry, this is the, this was already the n equal 2 starts from, sorry, this is the n equal 2, okay? So it goes like this. And then for all the n's, you have a picture like this. This is n equal 2. N equal 3, and 4, and so on. And then you have the limit, the Lagrangian limit, which is constant. But then at the same time, you also have the multi-critical versions that now we have described them in the multi-critical versions will be 0 until 3, and then they will come up and somehow they live only in the middle. But here there is also n equals 0. And actually n equals 0 survives to 2 dimensions. And so n equals 0, it's really a non-trivial CFT. And also here, if you look at the n equals 0, this will survive. Non-perturbative. So basically, it's really true. This, for example, this will be the class that we call the Triclitica ON in the limit where n goes to 0, goes to something non-trivial in 2D, right? Which, again, I'm sure that one can realize it by putting some further type of interaction in the kind of random walks or these kind of things. And then you can do this for any order of criticality. Yes?
What does it mean to add goes to 0?
Yeah, this is the map of the gen. So I don't have time here, but you can show that the criticality of the self-avalanche random walk can be mapped in the criticality of the ON model when n goes to 0. Okay? It's basically something which resembles the replica trick. In particular, you know the replica trick. So when you have disorder, for example, in the Potts model is more clear. When you want to treat the problem with disorder, one of the analytical techniques that is used is the replica trick, which is basically a way in which you create artificial copies of your system, and this artificial copy of your system will have a symmetry, which is a mathematical symmetry of the method, but it's, for example, in the case of percolation, is the permutation symmetry. So, but then you know that this is a symmetry that you used for computing the average over the disorder, and then you want to send this parameter equal to 0. This is something which is the basis of the replica trick. Is what has been used, for example, by Parisi to solve the Edward-Anderson model or the spin glass. So it's something very interesting that where these symmetries, they are not physical symmetries, but they are like mathematical symmetries that the problem has. And this is basically the source for this kind of mappings. The reason why you can have described something which is, let's say, a geometrical probabilistic problem in terms of a field theory in a particular limit. So this is a material of another course. If you don't know it, it's obvious. But I'm just mentioning it here because this is the reason why, even though the multicritical version of the ON model exists only in a range which is, fictitious in a sense because it's fractional, this is true only for the n bigger than 1. But n equals 0 really leads to something. So this exponent that we compute in this limit, they are exponent for a real conformal field theory. Okay? And yeah, then there has been various activity also recently, and we will intersect this activity also when we classify the universality classes at fixed n. There is this ON symmetry that can be realized starting from the critical 6. That is a theory that has been investigated a lot by Klebanov and Jombi in many papers. And actually we recover that. We will recover that when we do the classification of all the universality classes with the critical 6 and 3 components. And one thing which is very interesting of this kind of theories is that they are perturbatively unitary in the sense that they have positive anomalous dimension, even if they come from a cubic interaction. And okay. And then what I want to show you next week is this part here, where really the higher multicriticality can be computed with and then seen also with a non-perturbative RG. Okay. So yeah, today will not be so long. Then, okay, now you can really say, okay, give me a symmetry, let's play the game. Now, the second, so what we're gonna do now, as I said before, there are two ways of thinking now. We can either fix the symmetry and so explore all the possible symmetries. And so we can start from the most general symmetry, which is ON, and then we go to the finite, which is the group ON. Then, since ON is the maximal symmetry for our universality classes, because it's the symmetry of the synetic term, then if there are lower symmetries, they must be subgroups of ON. If they are subgroups of ON, two of them exist for every n, and they are the family which, in the language of polytopes and regular polyhedra, they are the n simplex, so the tetrahedra and the hypertetrahedra, which are, so the symmetries of so basically the tetrahedron, which is one of the 5 Platonic solids, exists in every dimension, okay? And so, since it is embedded in the sphere, the symmetry of this is one of the biggest subgroup of ON. And so, if you think that you want to follow symmetry, this is the first one you will consider. The other subgroup of ON, which exists for every n, is the hypercubic symmetry, or the one of which is dual to the octahedron, no? And this exists in every dimension. Then there are another kind of, so now you understand that one way to think about the subgroups of ON is the way in which you think about the geometrical objects, which are regular. So you also have the polygons, the diedral groups, which is another family. And then you know that when n is equal to 3 and n is equal to 4, so only with this type of representation, so only for this particular value of the number of components, you have additional structures. And so the additional structure you have when n is equal to 3 is the subgroup, which is the one of the dodecahedron or the icosahedron, okay? And when you have n equal 4, you have other two, which is like the 100 cell, the 600 cell. So in this particular n, you can construct some non-trivial subgroups and so on. So so after the ON, the most general family is what we can call the Platonic field theories, which are the theories that have the symmetries of regular objects, which means of all the possible subgroup of ON, there are some specific finite ones, okay? And we're going to do this also next week in generality, because now the problem becomes really a problem in group theory, because now the question is, okay, let's say that I choose, so in the case of ON, we have only one invariant. Our invariant is 1/2, phi 1 square, plus phi 2 square, and so on. So this invariant, so you see that I can have the square of this and I can have the cube. So I have, which means that, okay, this is the master, but the fact that I have the square means that there exists a theory of this type. And if I tune this parameter to 0, there is a theory with these types. And so this is the one that we were just looking at. But now if I choose a symmetry which is more complicated, for example, the icosahedral symmetry, well, you will see that the first invariant which differentiates from ON is of order 6 fields. So it means that you cannot construct a theory with icosahedral symmetry in 4 dimensions. Okay, but you can only construct it. So the only field theory that has that symmetry will be one with the critical, sorry, this is the critical 3. The critical 3, okay, and applying the master formulas for that. And this will give you all the RG information of that. Now, the problem of constructing invariants given a symmetry is not really a trivial problem, but luckily mathematicians have worked on that for a lot of time. And we will see there is a very nice tool that we're going to use, which is called the Mullion Series. The Mullion Series is basically a way to encode in a generating function all the information about invariants. So for every symmetry, we are going to write down a series with a specific algorithm that is based on the representation and other properties of the group, that has the property that when you expand this series that has in a power series, the coefficients will tell you how many invariants of a certain order I can construct. And so by using this table, with this machinery, we are immediately able to say, okay, all this to assign to a given symmetry, the beta functional will have a meaning. And so
is this something like a Hilbert series?
Huh? It's the Hilbert series, yes. Hilbert series is, when you do that for rings, you call it Hilbert series. I think that originally was done by Mullion, so when you do it two groups, it's the thing where you have the 1 over the determinant of summit over all conjugacy classes and so on. Okay, and so this is now what the kind of thing that we can do and that we're going to do. But before that, together with Johan, the first kind of symmetry that exists in every N is the permutation group symmetry. So the group of permutation, and so we have N fields. So this is the permutation group, which is, is the symmetries, for example, S3. S3 is the symmetry of the triangle. Okay, so the triangle is embedded in R2. So we have it's n equal 2. You need two fields. Okay, so there are two invariants, rho and how do you call it, the other one, and tau. And so now we have to do the same thing, but now the fact, one important thing is that one of these invariant, tau, so this is the number, this is phi square and this is phi cube. So the fact that it's phi cube tells us that the critical is equal to 6. And the fact that the critical is equal to 6 means that the beta functional we have to consider is this one. And the anomalous dimension of the system will be given by this one. Okay, so this is the way which you think now. And for example, as I for n equal 2, clearly rho is the ON invariant, or 2 invariant. But now you see that tau has a non-trivial structure. So it really becomes the, let's say, part of our job to find out how to realize the symmetries. And so you see that now the potential will depend on these two things, rho and tau. And you can check explicitly that these things are invariant on this thing when it's represented in a two-dimensional representation. And now you do exactly the same operation of writing everything in terms of a potential that depends on tau and rho. And so now you just need to do the algebra. So this is, but this more complicated formula encapsulates the fact that this is a less bigger symmetry. Because the smaller is the symmetry, the more complicated are the beta functions. Up to the point that when we don't impose any symmetry, we have the most complicated system of beta functions, which is the other approach that so this is very nice. So you can do this, and in particular then this universality class, when in statistical mechanics we call it the Potts model universality class, because the Potts model is a model in statistical mechanics, so it's very well known, and it has the property the underlying symmetry is Sn. Okay, so we call it the Potts universality class. And okay, the Potts universality class is something that belongs to the, let's say, the heroic periods of the Epsilon-Expansion. It's very well known, and then you can do an exercise that here you easily reproduce all the results of the literature. And in particular here, so to do something new, now we can do you see, while for the ON case, we were in the situation of using the n-component version of the even family, for this symmetry, we are forced to use the n-component version of the odd family. So it means that the next invariant we can write, sigma, is something that has 5 fields. Okay. And when I go here, then this theory exists in 10 over 3. But 10 over 3 is bigger than 3. So it's a candidate. The theories that I can realize in this way, they are candidates to exist in 3 dimensions. And so here things start to be new, because not only this 10 over 3 was never considered, even in the one component case, even less now. And so then I'm not now, today we are skipping the details in a sense, because the question is now, how do I construct all these invariants? Because, for example, we can use the Mullion series to enumerate them, but then we still have to construct them. And there is a very nice way that we do next week, and we do it also with the code, which basically allows you to construct the invariants in a general way by knowing the coordinates of the geometric object that has that symmetry. And so here I use this versor which are basically the vectors that point here, right? Two of these vectors. Okay, you have two of these vectors. You construct these kind of tensors. Okay, you symmetrize them in a certain way, and you contract them with the field, and you can prove that this generates the invariance. For example, the invariant that I showed you before, the explicit construction for tau was made in that way. And we can write it in mathematics, we can write nice tables of all these invariants, which really starts to be non-trivial, because it's really a non-trivial job to find the invariants given a symmetry. Okay, now let's do this. Now we know that in the logic we have to choose this upper critical dimension. So we have to use this beta function, which we are lucky because, again, it comes from our three-loop calculation with these strange gamma factors. Here I have actually those strange gamma factors. You can always redefine the field and send them away. So they're not really so important. Okay, you do that, and now you plug this potential inside here. You write some algorithm to do all these contractions in a recursive way, and you come out with a set of genuine beta functions. And now you start seeing the complexity of the problem of finding all universality classes, because here it's nice. It's a nice theory that has two marginal couplings. So while with the ON theory or with the standard Potts theory, we had only one marginal coupling, because the leading operator, there was only one invariant. Now there are two. And so you start having a set of two beta functions that depends on your external parameter, and which start to create, the complexity of what is universality when there is really symmetry playing around. And so this is the set of beta functions, which again, probably you will have never computed them if you had to compute everything from scratch every time. But here, and then it depends on the parameter. So what is interesting about this parameter is that, as I said to you before, the Potts 1, so when n goes to 1, okay, this universality class is the universality of the problem of percolation, which if you want is the simplest kind of phase transition that you can construct. And there is even a simpler version when n goes to 0, which is another statistical geometrical model, which is called the spanning forest. All this go under the name of random cluster model, something which also probabilists are working a lot. But this is nice because in any case, we can use this formalism. So this is another way to construct a quantum field theory for a geometrical problem. And actually, I have to say that these are the two interesting cases, because the case of the three-state Potts model is a case, one of those cases where the theory goes first order. Okay, because the three-state Potts model becomes first order somewhere above 2.5. So what is really interesting here are these two limits. Again, we have the system for all of this, and okay, then you can solve, and in particular you see something interesting. You say that for the three-state Potts model, which is n equal 2 and higher, we don't find any fixed point in 10 thirds, so a little bit above 3. And this is consistent with the idea that the standard Potts model becomes first order because the fixed point of the standard Potts model, the fixed point of the multi-critical Potts model collide somewhere above 2.5 dimension. Because now that we have more fixed points with multi-components, there is a new non-perturbative phenomena. This is something that the Epsilon-Expansion cannot do, and you really need other methods, and these are really complicated problems. Sometimes theory becomes first order because a fixed point and a one which has a higher multi-criticality because of an obvious reason that the flow comes out from one, they merge and become a complex pair of conjugate points. And so they disappear, and this is really one of the non-perturbative phenomena, because if you want fixed points, we are relying a lot, and our understanding relies a lot on the fact that fixed point branch from the Gaussian. In all our scheme, at the critical branch, but then there are other mechanisms. And the mechanism could be when two fixed points collide and disappear in this way. So the idea, it's a conjecture because it's not proven, is that the Potts model and the multicritical version collide somewhere. So if this is true, then we should not be able to find a little bit above 3 the multicritical version. And this analysis is consistent with this scenario. It's clearly not conclusive, but it will have been more problematic to justify a fixed point for 2 components with multicritical SN symmetry, S3 symmetry, and there's not there. But we have a multicritical point with percolation or spanning forest. And so these are probably related, and actually it's an open problem to understand. Actually, this is one of the most interesting open problem for me. Now, there is a fixed point when n is equal to 1. So this will be a more complicated version of percolation. The idea is that this universality class could be correlated percolation, which is percolation on Ising clusters. So if you know the problem of percolation is a problem where you have, you have grid, and then you, with a certain probability, you color a side, okay, with probability P, and you say that the system percolates if you can join this side and this side, okay? So if the current can flow and so on. Now this cluster are, in the standard percolation, you throw a coin for each one. So these variables are independent. Correlated percolation is a problem where the clusters are generated by some other random process. This random process could be, for example, the Ising model. So this will be a more critical version of percolation. These universality classes exist. The system can be simulated. Now the question is, which one is the field theory? And again, here we are in this place where we are using field theory in a smart way to characterize random systems by using these non-trivial limits. And we don't have time here, but the way to prove that the n equal 1 is percolation is exactly the replica trick. So you apply the replica trick to the problem of percolation. The replicas will have permutational symmetry, okay? But at the end, you have only one original field of your problem. So when you do this replica trick, you expect that, and since the RG quantities have always shown to be robust to this, and this is, for example, another study that we did on the ON model when n goes to 0. Since we were able to compute the critical exponent for arbitrary n, we were seeing that this limit is actually continuous. There is no jump. It's really something that you can draw, and clearly with the accuracy of theoretical physicists you can accept. RG quantities used to be continuous, and so you rely on the idea that, okay, if I study this system of finite n, I look for the fixed point, I compute the critical exponent, and then I send n to 0 or n to 1, this thing should be the critical exponents that characterize these two theories. Again, this is an intriguing scenario because here we are working with a problem with d critical equal to 10 over 3 and 10 over n, which means that if I take epsilon, I need to take epsilon equal to 1/3 to reach 3. So maybe this is a situation where the Epsilon-Expansion is well behaved. The Epsilon-Expansion has the problem when you use it in the critical 4, if you want to go to 3, which is the first useful place where you want to have quantitative information, is epsilon is equal to 1, and we know that it really doesn't converge. You can borrow a sum, but okay, it's not a definitive result. But here we are in this new situation where the upper critical dimension is just a little bit above 3 because it's a fractional upper critical dimension, and there are sensible universality classes. So if one finds out exactly which is what universality class, can really think of making some nice simulations and even maybe going to the next order in the loop expansion and characterize completely this kind of theory. And okay, so doing a little bit. Okay, so this is what I wanted to do today, because next week I want to do more hands-on stuff. Okay, so to recap what we did today: the master formulas, which is really the the reason for doing the functional approach, and rapidly we recover everything we know, and we can even have some first new stuff. But now we are really in the general scenario. So we can really say, okay, now I want to open a theory book, a group theory book, and say, okay, for every theory I want the field theory. And I can just almost do it actually, I'm sure we can just write a code. Actually, it was, you take the character table of that group, and from this information you have the beta function and the spectrum. It's like if you are adding a column to the atlas of groups, which is the atlas of universality classes. I think something fun. Clearly, many of them could be really of interest. And this is the approach which is symmetry based. But then, as we have seen here now, we were seeing a general pattern. We were seeing the pattern that if I take a smaller symmetry than the maximum symmetry, so with the maximum symmetry I have only rho. Now, if I take a smaller symmetry, I pay the price and have more invariance. My beta function becomes more complicated. Well, what is the system when I don't have a symmetry? I don't assume symmetry. Now I can treat also that problem. And the number of couplings, the number of independent, so the number of couplings there is a maximum value for each n, because basically if I don't have symmetry, if I, for example, say n is equal to 2 and I take d critical equal to 4, then I have this invariance. So my marginal potential can be written like this. Okay, so I have 1, 2, 3, 4, 5 couplings. And so I have a system of 5 beta functions. I will still have to factor away the general ON symmetry, but then this gives me a specific set of beta functions. And now the solution of that beta function is the most general n equal to k's. So if your symmetry is a solution of this system, it can exist. Otherwise, it simply doesn't exist. So now we are really going this way. So in particular for n equal, so n, and this is the number of couplings, let's say. So n is equal to 2. Here we have 5. 3 we have 15, and 4 we have 35. So this problem, we will see, we can solve it brute force. This problem is the thing that we have solved by smart use of the representation of the groups, subgroups. This is something that we have only numerical results for a limited number of solutions, but where we have found some new universality class with 4 components. But the general problem that, this other line of research where symmetry emerges, the general problem is that how can I find all the solutions? And I think that this is what I'm doing the research now on this thing. So, and what my way of thinking is that, okay, I know from one side that the symmetries must be subgroups of one. Subgroup of one, they can be complicated. And actually we have the complete enumeration in 3, 2 obviously, 3 and 4. But already in 4 is tricky. And actually there were some works done by Michel, by Berezin, by Zinjusten in the 80s, where they worked out starting from the subgroups of N4. But actually it turns out that they were working on, I realize now, on enumeration of the subgroups which was incomplete. And there is a nice enumeration done by Conway that I was studying that is a little bit more complete. But then you can also have continuous subgroups because you can have products of the 2. So in a sense, the idea is that you should, so the symmetry should belong to that basin of possibilities, but at the same time, these are polynomials. So this, for example, for the critical 4, this is our equation with squared equations, okay? Because the beta function are lambda squared. So somehow here you expect 10, here you expect 30, here you expect 70 solutions, no? They are actually less because you have to factor away the ON symmetry, the overall ON symmetry. Then it turns out that many symmetries are product of symmetries that come from the lowest order. So for example, in the 2, in n equal 2, we will find Ising times Ising and O2. Okay, so this is not a reducible case. It comes from a previous case. So many of these solutions are actually trivial. So the question is, can we use this? Can we factor away the trivial ones? Can we use the ON symmetry to reduce this number? And then can we intersect this with the known enumeration of subgroups to come to prove, for example, the goal will be because we have done the complete enumeration of n equal 3, the complete enumeration for n equal 4. The complete enumeration for general n, I think, is really hard because it will, I mean, the group theory side doesn't even give you the grounding for that. But I think, for example, the n equal 4 is a very defined problem, which maybe is under the reach of solving it. And I think it's very interesting because with n equal 4, you really start to see the complexity of the possible symmetries that can emerge. And this is nice because now this is the situation where the RG is bigger than symmetry. Because by finding the solution of this equation, we are computing the possible symmetries which are realizable in nature. And this new perspective is very intriguing because maybe one can speculate, are all the symmetries that we have computable in this sense? For example, the symmetry of the standard model or other kind of symmetry. Can they be realized? So now we are working with the scalar theory, but imagine now that we put inside gauge theories, fermions, and everything. And I mean, is the standard model one of these things that come out? Which are the other possibilities? Maybe there are not so many, because in any case we have n is equal to 4, but then we have some other constraint. So maybe we find out that the standard model is not really, is one of the few choices, or maybe not. So there are, I think that in this change of, because as today we were thinking that we have symmetry and then we have RG, no? We impose some symmetry and then we do the RG, but now we can switch the thing. So next week, now we have done all this week was more the theory. Next week I want to do some more research stuff. So I want to try to show you some computation, go through some of this one for the Platonic field theories to show you how systematically study all this and how to use the group theory arguments to understand which field theory goes in which dimension and so on. We can play a little bit with the ON, multicritical ON, and then we can look at the general classification. The easy case n equal 2, we can work out everything, and then we can maybe even do like a brainstorming lecture to have some ideas. Okay? Okay, we're done for today. Yes?
Are there cases here in which you can have some conformal window or fixed points are just isolated?
Yes. This is an interesting question. So normally the conformal window comes from an interplay of leading and extra-leading order, no? So you can do that here, and actually we have never done that, because for the moment already the problem of looking at the fixed point that emerge directly from the leading order is a daunting task. But yeah, for sure you can play that. You can play that, and I'm sure that there are a lot of things that can be done. And if you have a specific model in mind, it's very easy to look at, because you have all the leading and extra leading contributions. So you just have to plug in your symmetry and play the game of the band sacks, fixed points, this kind of things. And clearly here I don't have fermions inside, but we have done also, for example, the Yukawa couplings. The Yukawa interaction are easy functionalizable, because you have an H of phi, and then you have your bilinear. And so you can play also with that. But yeah, it's something that one has to look. It's an interesting topic.